Today's topic is multi-objective decision making problems. This is a kind of optimization model where we are dealing several objectives together and the objectives are conflicting in nature. In reality, we have seen that in any decision making situation, though we are considering that there is only one objective in the mathematical model, but in reality we could see that this is very much unrealistic, because all the time we are having the situation where we need to take several decisions together and decisions are conflicting in nature and we have to take the decision under certain constraints. That is why in optimization technique we are dealing with multi-objective decision making problems. Now today I will just introduce what is the concept of it. The subject is very vast and within a class that is very difficult to cover many things together, but I hope with this introduction if anybody is interested further they can go. That is why I am dealing with the situation where we are having several objectives together. For example, we are having a situation we have to take a decision. There are 5 options for us. There are flight from one place we are moving to another place. The source and destination that is fixed, but we are having several options in front of us. And for individual flight options, the travel time and the ticket price both are given. Now, in this situation, we have to take a decision that which flight should be selected where the travel time is minimum and the ticket price is minimum. That is obvious, we do every day without knowing multi-objective even. We are taking 2 decisions together which are conflicting. You see, I say again and again the objectives are conflicting in nature because you see we do not have any option where we will get the travel time minimum and the ticket price minimum, because the data has been given in such a way that you see where the travel time is high then the ticket price is low. That is why in this situation taking a single decision, if I ask you what is the optimal solution in this decision making situation, very difficult to find out the optimal solution because there is no single optimal in this case. That is why we say this kind of problem as a multi-objective decision making problem. One objective is minimization of travel time and the second objective is minimization of ticket price. If we just minimize the travel time, then ticket price is going up, and if the ticket price we are minimizing, then travel time is going up. That is why in this situation we have to take a decision which one should be selected. If I just draw it in a 2-dimensional space where x is x axis as a ticket price and the y axis as a travel time, then we could see that if we just put all the flight options, that is the travel time 10 hours with the ticket price 5700, if we just put, then you see we could get this as the option A, this is B, C, D, E. Now, if we consider geometrically even in 2-dimensional space, if I ask you which point is best point when we are minimizing both, very difficult, because you see if we say A is minimum with respect to x, but it is maximum with respect to y. C is somewhat minimum with respect to x, but still E has a good option than C with respect to y. That is why in this situation which one should be selected, that is a difficult part. Let us try to compare. You see we are having the data in front of us again. Let us compare A and B. Within A and B, which one to be selected? A and B cannot be compared, okay, because minimum travel time, ticket price minimum we won't get from here. If we include the option C, then we could see within B and C, certainly C is the good option than B. But once we are coming the comparison with A and C, it cannot be compared again, because travel time minimum and the ticket price minimum, either A nor C, nothing is accepted to us. That is why we could conclude that B and C can be compared, where C is the best option. Now, let us compare D and E. If we compare D and E, then E is the best choice than D, alright. But if we just include C within that, or B or A within that, you see we cannot compare. That is why from here we can summarize the situation in this way, that within D and E is more preferable, within B and C is more preferable, but A, C and E, these three options are not really comparable. Okay? This is the conclusion only we can make. That is why if I ask you, you put your choice in a rank, then in order, then what you will put? You will put probably any one of these three, A, C and E I will select, and in the next my choices will be either D or B. Okay? This is the case. If we just again come back to the figure, you see whatever I said, that has been given with the lines as a rank. Since we are going for the minimization, that is why again I am saying that A, C and E, these three options are not really comparable. That is why we are putting together in one rank, and B and D, within them these are not comparable, but these are not preferred with respect to A, C and E. That is why in this subject, this multi-objective optimization problem, you could realize that this is the situation day to day we are facing, but this is a subject where we are not really interested to find out the optimal solution. We are calling it as a Pareto optimal solution we target. Now, the word I uttered, that is the Pareto optimal, instead of optimal, this has been invented by the scientist the Pareto, and in his name only the name has been given, the optimality has been given as Pareto optimality, and our target is to find out that which are Pareto optimal to each other. Now, in this structure, if we just go, we talk about the dominance here, because you see A, B, C, D, E, in dominance term we will say that B is dominated by A, B is dominated by C, B is dominated by E, but B and D both are incomparable, both are equally acceptable to us. Similarly, A, C and E, these are dominating B and D, but A, C and E, these are incomparable. No one is better than the other one. Okay? That is why in the dominant structure, all are in the same level, and B and D are in the same level. That is why we have summarized the situation in this way: B is dominated by C, D is dominated by E, neither is better than the other for A, C and E. Okay? Let us go to the next situation. You see, we are having 4 cars. Now, car 1, car 2, car 3 and car 4, 4 models are there. Now, we have to take a decision which car is more preferable to me. Now, there are certain criteria to select the car model. One is the price in lakh, another one is the consumption, that is very much important for us whenever we are considering the mileage of a car, and what is the power of the car, that is also very much important. That is why if I just look at these 3 criteria, and with respect to that we have a table where we are given the options of different cars. If we target less price, more power and less petrol consumption, rather the mileage will be more, in that case if I ask you which car to be selected, with this dominant structure, try it out. Okay, I would say that the way I have said, you just think about it and summarize that which car will be the best car for us. If you cannot take any best option, go for the Pareto optimality, go for the dominant structure, go for the ranking of the group of cars. That is also quite possible, and we do every day without knowing multi-objective programming theoretically. Okay? That is the basic idea of multi-objective programming. Now, you see, we have a data set. We are having the data that there are two objectives F1 and F2, and there are 5 options A, B, C, D and E. We have to maximize F1 and minimize F2. That is our target. Now, you see, one thing is clear here, when we are dealing this kind of problem, you have come across the situation of linear programming, non-linear programming. Everywhere you have seen that we were having several options in front of us. You have come across the situation where the feasible space is consisting of infinite number of points. Infinite number of feasible points means infinite number of alternatives in front of us, and infinite number of options are there in front of us. But here in this situation, you just notice that we are having very much finite number of options, only A, B, C, D or E. Any one or a group of objects we have to select. Okay? That is why the situation is little bit different than the previous situation. But again the optimization problem, we have to maximize F1, we have to minimize F2. Now, in this situation, how really we deal with? If I tell you, just do it. Just I showed you the problem of car example. There you were having 5 options or 4 options there of 4 car models. Now, if I ask you draw it graphically, very difficult for you, because in 4-dimensional space you can visualize, but you cannot draw. Okay? That is why those kind of problem how to deal, I am just showing you, because through figure, through graph you cannot do it. Graphically you cannot solve, you have to solve it manually. That is why I will tell you how to prepare the dominant structure when we have several objective functions together and we are having finite number of alternatives in front of us. Now, what we do? We just prepare the table in this way. I will just prepare the table for you, then I will explain the thing in detail. Now, you see, we are having 5 options A, B, C, D, E. Similarly, A, B, C, D and E. What we have targeted? We have targeted maximization of F1 and minimization of F2. Okay? Now, look at the data set, this data set. Just compare A and A. If I compare A and A, nothing can be said because both are equal to me. If I compare A and B, I will just put a tuple. Tuple is a combination of few elements together. Here I am putting a tuple of 2 elements within the parenthesis. Okay, one is for the preference for A with respect to B with respect to F1 and A with respect to B with respect to F2. If A is it that A is preferable to B with respect to F1? Not really, because we are maximizing F1 and the value of A with respect to B, A is 8 and B is 9. That is why with respect to F1, A is not preferable to B. I am putting the minus sign there. Now, let us see for F2. With respect to F2, we are trying to minimize F2. For A the value is 5 and for the B the value is 2. That is why A is not preferable to B with respect to F2 again, that is why I am putting minus. But if I just compare B with respect to A, what we could see that with respect to F1 B is preferable to A, and with respect to F2 B is preferable to A as well. Okay? In this way, if I just compare A and C, just look at the data 8 and 12 with respect to F1, that is why A is not preferable. With respect to F2, A is not preferable. Okay? And similarly, we can do for AD, AE, we will get the same result. A will not be preferable than B, C, D, E at all. Alright? If I go B with respect to A, we have seen this is preferable for both the objective functions. Now, B with respect to C, if we do maximization of F1, that means B with respect to B, nothing. B with respect to C, then not preferable, and C is also not preferable. Okay? In this way, I will just complete the another component in the matrix for you, then I will just summarize everything through my screen. Now, B and D, just you see B and D, with respect to F1, B is not preferable, but with respect to F2, both are coming the same value 2 and 2, B and D, that is why we will put equal to. Okay? In this way, if we just do the entire table, just you see, if I just do the entire table with plus and minus combination, then an equality combination, then from here we can summarize the entire situation and we can put everything at a glance. We can take a decision which one is preferable, which one is not preferable. Now, you see, if we are having 4 options instead of A, B, C, D, E, 5 options, but if we have 4 objectives, then we will have a tuple of having 4 elements together. That is why with plus, minus and equality, we can put all together in front of us. And from here, we can summarize that A is dominated by B, C, D, E, because all are having minus. Okay? Look at B. B is dominating A, but B is dominated by C, dominated by D, because one of the option is minus, though one is equality. That is why B is lower preferred than D. Okay? And similarly for E, and C and D, if we just compare C and E, if we compare, you see C and E, these are non-dominated to each other, because all are having either plus or equality. If both are equal, equal preferable. If plus, preferable. That is why we cannot really compare in general here C and E. And what about D? D is dominated by few and dominating few. This is the situation. That is why which one will be put as the rank 1? If I ask you, then C and E both are non-dominated to each other. That is why I will put in the rank 1 C and E together. Now, C and E I am keeping aside, and I am again comparing A, B, D in the similar manner, and we could see that A is dominated by B and D. That is why A must be in the last rank, and within B and D, if we just compare, D is more preferable than B, because in B there is one minus. That is why I will put D here and A here. That is why if I just summarize everything together, we could see that we could group A, C and E together in one rank, second rank D, third rank B and the fourth rank A. Okay? But nothing I could say this is the optimal solution. I would say that C and E are Pareto-optimal solutions. We will say that C and E are non-dominated solutions. We say Pareto-optimal solution, non-dominated solution, efficient solution. These are all we use interchangeably, because non-dominance concept the mathematicians they like very much, because all the time we are talking about the dominance, we are talking about the total ordering, partial ordering. That is why the mathematicians prefer the term non-dominance. We say it both the solutions are non-dominated to each other, both are non-dominated solutions. But economists they prefer the term Pareto-optimal solutions, because the Pareto, he is an economist and he has given the name, and according to by his name only people, economists they prefer the term Pareto-optimality. We will say C and E both are Pareto-optimal solutions in this situation. But the management scientist people they are more habituated to the term that is the efficiency of a portfolio option, whether this portfolio option is efficient in the market or not. That way they view. That is why the management scientist people they call it as efficient solutions instead of non-dominated solutions or Pareto-optimal solutions. But non-domination, non-dominated solution, Pareto-optimal solution, efficient solution, all are equally means, because all are accepted equally. I would say that C and E both are non-dominated solutions, both are Pareto-optimal solutions, both are efficient solution. This I have shown you the option where we were dealing with the situation we were having very much finite number of alternatives. Now, I am moving to a situation where we are having infinite number of alternatives. Okay? Just read the problem, just to see the language of the problem. There are two products and we need to maximize effect on balance of trade and the profit together, and we are having certain constraint set. Now, you see here the constraints, these are having the linear structure we are having in the constraint set, okay, and objective functions again the linear. That is why if we just draw it graphically, because you know the linear programming you dealt with the graphical solution. That is why let us try to draw the graph of this problem. Then we could see that the first one is minus x1 plus 3 x2 less than is equal to 21. That is why if this is x1, this is x2, one line this could be this way. Okay. The second one x1 3 x2 27, that is why one line will be this way, and less than equal to, that is why certainly this region we are considering. This way if we just draw 4 constraints together, then we will get this picture. These are all the 4 constraints together, and this is the feasible space for us. Now, you see there are 2 objective functions. One objective function is minus x1 plus 2 x2. This is one objective function, and another objective function is there, that is 2 x1 plus x2. If we just draw it, this is the feasible space for us. All right. Now, minus x1 plus 2 x2, it means that is the, we could see that this is the slope of the f1, all right, the red color, this is the slope. If it moves this way, then ultimately here I will get the optimal solution, because maximally the objective function can move this way after this it will be out of the feasible space. Okay. This is for function 1. If we do for function 2 the similar thing, then we could see that no, this is not 2x1 plus x2, that is why it would be this way. If we could see this way, if the objective function is moving, we will see the optimal solution will come here. All right. In between, just you see in the screen, it is there. This is the first objective function, this is the second objective function. Okay, this is the situation for you. Now, if I ask you which solution then we will take, we are maximizing both together. We are not getting a single option, we are getting an option one for first objective function this point x1 and for the second objective function x4. Okay. Look at more about it. You see, when we were moving, we were just to think that we are walking through the edge of the feasible space. Okay. I am moving from x4 to x1. What we could see that second objective function is reducing further and further if I move through this line, through the edge of the feasible space. Okay. My second objective function z2 value will not improving, it is the value will be minimizing, because if I move this way other way x1 to x4 objective functional value will be increasing, but if I move from x4 to x1 the objective functional value will be decreasing. But in the other case, if I just look at the first objective function, if I move from x4 to x1, first objective functional value is increasing, whereas if I move from x1 to x4 through the edge of the feasible space, if I just walk through the edge of the feasible space, the z1 value is decreasing. That is why through this edge z1 is increasing, z2 is decreasing at every point. That means, I cannot have a single option where both the objective functions are maximum. I can select any one. If I select this one, then I have to compromise with z2. If I select x4, then I have to compromise with z1. Similarly, if I just go at point x2, I have to compromise z1 a little bit, but z2 more. That is why I cannot really take a decision from x1 to x4 if I just walk through the edge of the feasible space, then which will be more preferable to me. I will say both are equally accepted to me, because if I improve one objective functional value, other objective functional value, for that we have to really compromise. That is why always there will be a trade off within this line. Okay. That is why all these points in the space, these are equally accepted to me. That is, in other way I will say all points are non-dominated to each other, Pareto optimal to each other, efficient to each other. That is why we can say that the points which are at the edge of the feasible space from x1 to x4, these are non-dominated solutions or Pareto optimal solutions or efficient solutions. Okay. Now, I hope you understood the situation. Okay. Though I have written it as efficient frontier, we call it as Pareto optimal frontier as well, and we say non-dominated frontier as well. Okay. The same thing. Now, let us consider another objective function. This is the unconstrained nonlinear programming problem, that x is moving within -4 and 4, but minimization of x square and minimization of x minus 2 square. If I just draw it, this is x square and this is x minus 2 square. All right. Now, what we could see that from -4 to 0, just let me draw it for you. This is x square this is x minus 2 square. All right. This is 0, x equal to 0 and this is x equal to 2, and x is ranging from minus 4 and plus 4. Let me just move through the x axis. If I move from minus 4 to 0, what we could see that this is my f2, this is my f1. f1 is decreasing as well as f2 is decreasing from minus 4 to 4, minus 4 to 0. Both f1 and f2 decreasing. All right. Now, this is the point, this point is as 1. If I move through 0 to 1, we could see that f1 is increasing, but f2 is decreasing. All right. Now, similarly, if I move from 1 to 2, f1 is increasing. Now, 1 to 2, f1 is increasing and f2 is decreasing, and from 2 to 4, f1 is increasing and f2 is increasing. Once again I am repeating, from minus 4 to 0, f1 is decreasing, f2 is decreasing. All right. From 0 to 1, f1 is increasing, this is the f1 line, f2 is decreasing, this is my f2 curve. Okay. From 1 to 2, f1 is increasing, but f2 is decreasing. Again from 2 to 4, both are increasing. This is the whole pattern. Okay. If I ask you that within minus 4 and 4, where is the trade off? That means one is increasing and other is decreasing. I cannot have a single option here. From minus 4 to 0, if I want to minimize both f1 and f2, certainly I will select this option. There is no doubt about it. From 2 to 4, if I ask you minimize f1 and f2 both together, for this point I will select f2. Okay? That would be the minimum value. But within 0 to 2, there is no single option. If I select this point, then f1 is lower, but f2 is higher. Similarly, here also the same. Within this space, I would say that there is a trade off, because within this range, both the values of f1 and f2, if f1 is I prefer f1, then I have to compromise with f2. If I prefer f2, I have to compromise with f1. That is why I would summarize, I would say that from 0 to 2, I am unable to take a decision. I will say from 0 to 2, all are equally accepted to me. That is why the non-domination will be there, Pareto optimality will be there from 0 to 2. Okay? And that is the non-dominated frontier or efficient frontier or Pareto optimal frontier. Now, from 0 to 2, I am giving you another example for you, that minimization of root x plus 1 and x square minus 4x plus 5. And this part I am keeping as an assignment for you. If you try it out, which part would be the where the trade off of both the objective functions are there, you just try to find out, because in x axis x is there, in y axis f1 and f2 both are there. Okay? And you find out which one, where the trade off is there for both the objective functions, then you can declare that is the non-dominated frontier for you. Thank you for today.